Right, you got the handouts, I hope. So I think we've probably got enough here for. We'll probably go over into next week with this handout anyway, but we'll see how we get on. We're going to carry on with the rules of differentiation this week, covering the quotient and chain rules, and have a little bit of a look at second and higher order derivatives, and then start to talk about rates of change, successive differentiation, working towards actually doing some engineering problems involving differentiation. All right. That slide was meant to have been taken out, but never mind. So we've got our table of standard derivatives that we've been using. I've kept those in just in case. You've got your whole page one anyway that also includes these rules. So we did the product rule last time, one at the top. Today we're going to look at the quotient rule and the function of a function. Okay, everybody happy with that?
Oh, it looks difficult.
So third, maybe it's a bit tricky, but it's not too bad. All right, so quotient rule. This is where we've got one function of x. So we've got y is equal to one function of x on the top for sine 5x. And then the denominator is another function of x, in this case 5x to the power of 4. Okay, now where it doesn't make too much any difference with the product rule, when you're multiplying, you must get u and v the right way round in a quotient rule. You must make the numerator u and the denominator v for the formula to work properly. Okay, so we get, in this case, we'll let u equal 4 sine 5x, and then we have to differentiate that. So du by dx is equal to, so if we differentiate 4 sine 5x, what happens? Anyone remember? Look at your table of derivatives for the sine function.
Times it, then, yeah,
A cos AX.
Yeah, so you take the 5 out and multiply, so 4 5s are 20, and then it goes to the cosine of 5x. Yeah. And then over here, what we'll do, over on the other side of my page, we'll say let v equal 5x to the 4 dv by dx equals, what do we do here to differentiate?
Tail nose.
4 comes down and multiplies, so 4 5s are 20. And take 1 off the index. Yeah, take 1 off the index. Okay. So now what we've got is we've got everything we need to put in this quotient rule formula. So we can go dy by dx is equal to, and we want on the numerator, we want v first, so 5x to the 4 times du by dx, 20 cos 5x, and then that's minus u, which is 5 sine 5x, times dv by dx, which is 20 x cubed. And then all of that has got to be divided by v squared.
Oh,
Where did
right.
you get 5 sine 5x from?
Oh, come on, mate. We've gone past that bit. That's the
1 minute. Du by u. Sorry, 4 sine 5x. Well spotted, that man.
oh yeah. Oh yeah.
Yeah. Okay. Am I correct now? Yeah. Everyone happy with that?
Yeah.
Right. We can bring together 5x to the 4 and 20x to the 3 to be 5 times 20 is 100. X to the 4 times x to the 3 is 1 minute. He's got oh no, it's minus, isn't it? I'm looking at what he's done here. Let's go our own way with a simplification. 5x to the 4 times 20, so we got 100. I can see it now. 100 x to the 4 cos 5x. So I multiplied 5x to the 4 by 20. Yeah. Minus 4 times 20 is 80 x to the 3 sine 5x. All that is over. 5 5s is 25. X to the 4 squared is x to the 8. Okay, and that is an answer that I would accept to that problem. Okay, everybody happy with that?
Beautiful.
Good. All right. So we'll have a look at another one more, and then you can have a go at one or two yourselves. All right. So here with the problem says determine the gradient of the curve at the point where x is equal to root 3, y is equal to root 3 over 2. So this is one where you've got to differentiate and then enter those values in to find out what the slope is at that point. Okay. So first thing we're going to do is just write out what we got a bit bigger. 5x on top, 2x squared plus 4 as the denominator. So we'd let u equal 5x, du by dx. What happens when we differentiate? What's the index of x here when it's just x on its own? It's 1. So if we bring 1 down and multiply, we end up with 5. And this becomes x to the 0. Any number to the power of 0 is equal to
0.
no
1.
1.
1.
Yeah. Yeah, it's 1. So we just drop the x off, it becomes 5. Du by dx is 5. On the other side, let v equal 2x squared plus 4 dv by dx equals, so if we differentiate this, 2 comes down, multiply 4, x to the 1, and then when we differentiate constants, they just disappear. So dv by dx is 4x. What we do now is put all that in the formula, so we can say dy by dx is v 2x squared plus 4 times du by dx 5x minus u, hang on, du by dx is just 5 minus u 5x times dv by dx 4x, and all of that is over v squared. V is 2x squared plus 4 all squared. Everybody happy? Follow that so far?
For dv over dx, why do you just lose that plus 4 again?
Well, when you differentiate here,
Yeah.
yeah, right,
Because it's a constant, isn't it?
yeah, just let me put that back how it should be. 2x squared. Just put a new slide up, right? We got 2x squared plus 4, yeah?
Yeah.
Y equals, okay? Now, when we want to differentiate that, we differentiate each of these two separately and add them together, right?
Yeah.
So this could be written as 4 times x to the 0 and still be the same thing because x to the 0 is 1, yeah?
Yeah.
All right, so differentiating this one, we do 2 times 2 x to the 1, yeah? That equals 4x. Agree?
Yeah.
And that's plus. Here, we multiply by 0 times x to the minus 1. Well, 0 times anything is
0.
0. Yeah. So constants like 4, 10, minus 6, any number you can think of, we differentiate them because you end up multiplying by 0, they disappear.
Yeah.
All right.
Yeah. Yeah.
Happy?
Yeah.
Yeah.
Thank you. Thank
Good.
you.
So if we then simplify here, we've got 10x squared plus 4 5s are 20 minus 20x squared all over 2x squared plus 4 all squared. No point in multiplying those brackets out. That's much simpler there. Yeah, as it is. Okay. Happy?
Yep.
Yeah. What we can then do is just This is dy by dx is equal to. Oh yeah, we got a 10x squared take away a 20x squared here, so we can finish up with 20 minus 10x squared on the top, all over 2x squared plus 4 all squared. Happy with that, everyone?
Yeah.
Yeah. So we've got to put, we got this extra information this time. We want to know what the slope is when x is equal to root 3, because it says find the slope at the point root 3 comma root 3 over 5. Yeah. So where x is equal to root 3. So what we do is we write this out, but everywhere we see x, we write root 3. So it's 10 times root 3 squared over 2 times root 3 squared plus 4 all squared. Yeah. If you put that in your calculator, you should get the answer. Just try it, minus 1/10.
Oh no, coronavirus.
Okay. Everybody happy with that?
Just writing it down real quick.
That ain't actually that difficult to do because root 3 squared is 3. So that top line becomes 20 minus 30. And the bottom line is 2 times root 3 squared, so that's 6. 2 times root 3 squared is 6. Plus 4 is 10. 10 squared is 100. So it's fairly easy. That's minus 10 over 100, which is a minus a 10. Okay. Right. In your notes, you have some problems involving quotients. So I'm going to give till 9 o'clock.
Can you just go backwards and get that last bit down?
Yeah, I'll do it in a minute. At 9 o'clock, have a go at 1 or 2 of those, please. See if you get the answers in brackets. There you go, Macaulay.
Record.
Right. Now the next thing we're going to have a look at is where we have the function of a function or a chain rule. So this is where we've got one function of x multiplied by another function of x. So in the case of this problem here, we've got, one function is inside another function. So what we've got here, we've got a cosine function. Hang on. So we've got a cosine function, and then inside the brackets of that cosine function, we've got 5x squared plus 2, which is a function of x. Yeah. So we have to use the function or chain rule. Yep. So what we do here is we let u equal 5x squared plus 2. Yeah. That means we can write y is equal to 3 cos u. Okay. And then we're going to differentiate 5x squared plus 2. So du by dx is equal to 2 comes down and multiply, make 10, 1 off the index. So that's 10x. Yeah. All happy? And dy by du is equal to, so there's no constant in front of the u, so it must be minus 3 sine u. So what we've got now, have we got all the parts to this formula up here? We've got dy by du, and we've got du by dx. So we can say dy by dx is equal to dy by du minus 3 sine u times du by dx 10x. All right, that is equal to minus 30x sine u. Okay, and then we put back, we take what we called u up here and put it back in there. So it's the final answer is equal to minus 30x sine 5x plus 2. Okay.
Beautiful.
Yeah. So although we always end up doing the chain rule last because you think that's probably going to be the hardest, that's actually the easiest one to do. As long as you can differentiate the two parts of it, it's not too much of a problem at all. Okay, everybody got that down?
Yep.
Right, on the next page, there's another one. Let's just have a look at that. Everybody happy? So it says determine the differential coefficient of y is equal to the square root of 3x squared plus 4 minus 1. What do you think we need to do here, guys? Anyone got any ideas?
Get it out of the square root.
We need to
Square.
write it as a square root differently. We need to say it's equal to 3x squared plus 4 minus 1 to the power of a half. Remember, we can write the square root as a power of a half. So what we've got here is a function of x inside the brackets, and then the square root is a function as well. So we've got a function of a function. Now we've done that, we can let u equal 3x squared plus 4x. Someone didn't spot my deliberate mistake. Minus 1, 4x minus 1. So du by dx equals 6x plus 4. Constant disappears. Yeah. We got y is equal to u to the half after we've made that substitution. Yeah. So dy by du equals half comes down and multiply u to the minus a half. All happy with that?
Get in there.
Yep. So dy by dx is equal to dy by du half u to the power of a half times du by dx 6x plus 4. Yep. Okay. Now, this u to the half here can be written as a half times 1 over root u. Yeah. And all of that is times 6x plus 4. Okay. And then that's actually 1 over 2 times root u times 6x plus 4. Yep. Everyone happy? And then we can put in our value of u from the first place. So 3x squared start again. One over 2 times 3x squared plus 4x minus 1 and that's the square root of, and all that is times 6x plus 4. Bit of a tricky one, that one. We just wanted to put that in because of the fact that you had to write the square root in a different way to be able to solve it. You all follow that reasonably well.
Yeah.
Hi, Logan. Didn't see you put your message in. I was in full flow.
No stopping Mike when he's in full flow.
No. Okay. All happy with the function of a function rule? on the next page, there are some examples for you to have a go at. All right, so I'll give you till about 20 past to have a go at them. All right. Good. If you have a quantity y, depends on and varies with another quantity x, then the rate of change of y with respect to x is the differential dy by dx. So other examples, if we got the rate of change of pressure with respect to height in a tank or something, we could have dp by dh. A rate of change with respect to time is usually just called the rate of change, with respect to time being assumed. So if we talk about the rate of change and it's with respect to time, you're normally talking like the rate of change of current is di by dt, the rate of change of temperature d theta by dt, and so on. Okay. So let's have a look. We'll have a look at our first real kind of engineering example. The length L meters of a certain metal rod at temperature theta degrees C is given by L is equal to, just write this out, L is equal to 1 plus 0.40 5 theta plus 0 and 6 noughts 4 theta squared. And it says determine the rate of change. So we're looking for what is dl by dt. Yeah, when we differentiate the constant 1, it disappears. Differentiate this part, it becomes just 0.405. When we differentiate this part, the 2 comes down, so it's plus 0.608 theta. All follow that, hopefully. Yeah. And then I, when theta is equal to 100 degrees C, dl by dt equals 0.30405 plus 0.608 times 100. That's equal to 0.00013 meters per degree C, equals 13 millimeters per degree C. Yeah. And then for B, we would just take this here and replace the away the 100 with 400, and if you try, your calculator should get 0.37 millimeters per degree C. Yeah.
What happened about +1?
That when we differentiated as a constant, gone.
Oh, so just leave it out.
So differentiate constant, it disappears. Okay.
Right, yeah.
Yeah. When you differentiate a variable to the power of 1, you just lose the variable. So on the 405 bit, you just lose the theta. Yeah. and then on the third term you multiply by 2 and take 1 off this index, so it goes from squared to a power 1. Yeah. All right, everyone.
Yeah.
Yeah. Right. Okay. Now, there's an important thing for me to point out to you here. We have a sine function, okay, in terms of calculus. If we have pi involved and sine functions, we must have the calculator in radians mode. Can't have degrees in terms of the sine function, cosine function in calculus. All right. So it's saying the displacement S of the end of a spring at time t seconds is given by S is equal to I times E to the minus kt sine 2 pi ft. What rule have we got to use to differentiate that function? Because the velocity is ds by dt, so we need to differentiate that. But what rule have we got to use? We've got a function of x here. There's a multiplication of another function of x. Product rule. Yep. We're also told that I is equal to 2, k is equal to 0.9, and f is equal to 5. Okay. So we can rewrite this as S is equal to I, which is 2, E to the minus K T times sine 2 pi times F is 5, so that's 10 pi T. Everybody follow that?
Yeah.
Then we can let U equal to E to the minus 0.9 T du by dt.
Where did the 2 come from?
Magic.
In front of the E.
That's, says in the question, Macaulay, I is equal to 2.
Oh, yeah.
Yeah.
Oh, you
Okay.
numpty.
No, not at all. Right.
I'm playing.
So when we differentiate here, what happens? In actual fact, you're probably better, in all honesty, to leave the function. I'm just going to get, sorry if you written all that down, but you're probably best to differentiate it as it is up here. So ds by dt is equal to, now the minus k comes down and multiplies, so it's minus ak e to the minus kt. Yep. Hang on, I'm going wrong here again now.
Oh no.
Sorry. Let u equal a e to the minus kt. Yeah. Du by dt is equal to minus a k to the minus kt. Yeah.
Before I write this down, are you sure this is the right one?
Yeah. As sure as I'm going to be. V, we'll let V equal sine 2 pi ft. Yeah. dv by dt equals 2 pi f, and that's a minus. No, that's a sine goes to positive cosine, doesn't it? Okay. Meaning that ds by dt is equal to u a e to the minus kt times dv by dt 2 pi f cos 2 pi ft plus, and then we want v sine 2 pi ft times du by dt, which is minus a k e to the minus kt. Okay. And I have to say that even in Mr. Bird's solution, he's left it like that. He hasn't tried to simplify that at all. So he's, there you go. I'm going to take that on a new page, I think. I'll let you catch up. So from there, so we go when I equals 1, k equals 0.9, and t equals 1. Yeah. Velocity equals ds by dt, which is, you've got to put I in. I is 2. So that's 2e to the minus 0.9 t times 2 pi times 5, which is 10 pi times 1. Hang on, we need a 1 up there as well, don't we? So that's t is 1, so that's just 0.9 in there, minus 0.9 in there. If that's times 1, I'll just take it away. And that's
Where does it say t equals
Hang on.
1?
here.
No, but in the question.
In the question.
It says f equals 5.
Find, determine the velocity of the end of the spring after 1 second.
Oh, right. Oh, yeah, I see
Yeah.
now.
Cos 10 pi times t, which is 1. Yeah. It's that bit. Plus sine 10 pi. So all multiplied by 1. Times minus a, which is 2. Times k, which is 0.9. E to the minus 0.9. Close the brackets. Close the brackets. All right. Now, if I got that right, and you make sure you use your calculator in radians mode, you should get an answer of 25.55 centimeters per second, and you put all that in your calculator. So differentiating 2 successive times ends up with the second differential. We can go on to the third, fourth, fifth, and so on. So if we take function of x as, so we got f(x) is equal to 2x to the 5 minus 4x to the 3 plus 3x minus 5. And it says find f double dash of x, find the second differential. So the first thing we can do is say the first differential, we differentiate 2x to the 5, we end up with 2 times 5 is 10, x to the 4, 3 times minus 4 is minus 12, x to the 2, 3 times 1 is 3, x to the 0, so we just leave it off, and differentiate a constant, disappears. So that's the first differential. And then we can differentiate again and say f double dash x is 4 times 10 is 40, x to the 3, 2 times minus 12 is minus 24, x, and the constant disappears. So there's our first differential. Second differential. And this one could also be written as d2y by dx squared as the other type of notation. You happy? Yeah.
I'm kind of happy. I just don't. How come the x goes from the 3x? So I know the constant
Right.
always goes, but how come you removed the x?
Right. I'll show you on another patch. So with, if I use the 3x you're bothered about, yeah.
Yeah.
So if we've got a constant 3 in front of x, yeah, we want to differentiate it. What index could I put on x with it, and that's still just equal to x, Macaulay?
1.
1. 1's the index we never write, isn't it? Yeah.
Yeah.
So if we apply the rules of differentiation, yeah, we come down, so we go dy by dx. Let's assume that y is equal to 3x, yeah? dy by dx is equal to 1 times the 3, and we've got to take 1 off the index, so it's times x to the o.
Okay.
Yeah, x to the o is equal to
0.
1 times 3 is 3, and x to the o is 1. So when you differentiate and the power is 1, the variable disappears. When you differentiate a constant, that's multiplied by x to the o. So you're bringing 0 down, you're multiplying by 0, that's what disappears. Does that clear that up?
Yeah, thank you.
Yeah. So on your next page, we got velocity and acceleration. Just let me have a look here. Yeah, we got time to do this, I think. Right, velocity and acceleration. So when a car or any other vehicle really moves a distance x meters in a time t seconds along a straight road, the velocity v is constant, and the velocity is equal to x over t meters squared, i.e. is equal to the gradient of the distance versus time graph. Yeah. So what we're saying here is velocity is the slope of the graph, or the rate of change of distance with time. Therefore, it's the first differential of distance versus of the distance moved in time t graph. All right. So if we've got a function of distance moved is equal to a function of x, then the velocity is equal to f dash of x, the first differential of that. Okay. Now, on the next page, when velocity is not a constant, if however the velocity of the car is not a constant, then the distance time graph will not be a straight line. It may look like that shell below. So in the previous slide, we saw that the slope of a distance time graph represents the velocity. If the line AB, as shown on there, the red line, is a tangent to the curve at x, then the slope of the line AB is the velocity at point x. So we can find the slope of the curve by differentiating the function. So if we had an expression for that black line, y is equal to a function of x to represent that x, that line there. If we differentiate that function, we end up with the velocity of the vehicle at point x. Everybody follow that?
Oh,
Probably
yes.
follow it more when we're done an example, but we'll see. Okay. If we then think about the acceleration I of a car, that is the rate of change of velocity. So if we think of velocity as the rate of change of position, or the rate of change of distance, then if we acceleration is the rate of change of velocity. So the slope of the velocity time graph, so if we've got a velocity is equal to function related to time, if we take the slope of that at a point, we get the acceleration. Yeah. In summary of what I've just said, and we probably have to flip back to this next week anyway, acceleration, acceleration is dv by dt, so we differentiate the velocity function, yeah, or we can differentiate the distance over time function twice to get the second differential of the distance function. So if we have a function distance equals f at time t, velocity is equal to f dash t, or dx by dt. So we differentiate distance once, we get the velocity. If we then differentiate distance again to get d2x by dt squared, we then have the gradient of velocity time graph, which is acceleration. So that's that distance moved, speed, or velocity, I should say, and acceleration relationship is the function, its first differential, and its second differential. Okay? I think what we'll do is we'll leave that there this week, and we'll pick up by summarizing that again next time, and then we'll do some problems around velocity and acceleration. Okay? Is everybody happy with that?
Absolutely beautiful.
If anyone got any final questions, either in the text, in the chat, or turn your mic on and speak to me.
No, could you send the handout for next lesson? Or are we using the same as last?
No, I will be sending that as soon as I have it ready.
Oh,
Fully.
thank you.
All right?
All right. Well, see you next lesson, Mike.
Yeah, see you at 2:15. All right?
Bye.
Bye, Mike.
All right.